I'm Thomas Dickinson, a PhD student at the Rochester Institute of Technology, Center for Imaging Science in the Digital Imaging and Remote Sensing Laboratory. My advisor is Dr. Michael Gartley. Today I'm presenting our research on automated 6 degrees of freedom satellite pose estimation from resolved ground-based adaptive optics imagery. Large ground-based adaptive optics telescopes produce well-resolved imagery of low Earth orbit satellites. This imagery is rarely used for pose estimation due to two main challenges: variable image quality and the labor-intensive nature of manual pose estimation processes. To expand on these challenges, computer vision methods typically struggle with the kinds of imagery we get from ground-based adaptive optics telescopes. It's often quite blurry with low signal-to-noise ratio and bright specular glints accompanied by extremely deep shadows due to the lack of atmosphere to scatter light onto parts of the spacecraft that aren't directly illuminated. It is also highly variable from frame to frame due to varying atmospheric conditions, adaptive optics system performance, and changing illumination geometry. While supervised deep learning with large datasets has shown promise in overcoming similar challenges for other applications, we face a significant obstacle. We have no real accurately labeled data for this specific application. For these reasons, despite research spanning 3 decades, previous work has been limited to estimating only 3 degrees of freedom rotation and only for fully illuminated imagery with artificially constrained motion. Furthermore, results for past approaches were only demonstrated on simulated data, never tested on real imagery. Our work represents the first comprehensive solution to the full challenge, estimating all 6 degrees of freedom pose from partially illuminated real imagery with unconstrained spacecraft motion. Given the lack of real labeled training data, we must turn to simulated imagery. However, this introduces another significant challenge. Deep learning methods often struggle when trained on simulated data and tested on real data, a problem known as the sim-to-real domain gap. In recent computer vision research, while learning-based pose estimation techniques have demonstrated superior performance when trained on high-quality imagery with real training data, performance drops significantly when trained on simulated imagery and tested on real imagery of variable quality. Our research aims to develop a robust methodology for automated satellite pose estimation that addresses these challenges. Specifically, we have 4 main objectives. First, develop a methodology to simulate large, diverse image datasets. Second, augment that simulated data through randomized image degradation to bridge the domain gap, incorporating double Gaussian blur, noise, bias, gamma, contrast, brightness, specular glints, and coarse dropout. Third, design and train robust deep learning models capable of real-time 6DoF pose estimation. And fourth, evaluate the speed and accuracy of our model on both simulated and real test data. We propose a 3-stage approach to solve this problem. First, the coarse localizer, a convolutional neural network containing approximately 20 million parameters. It takes the full-frame image from the telescope as input and predicts both the amodal full object bounding box and center coordinates of the satellite. We use a U-net architecture to predict a binary amodal object mask, which helps handle partial illumination conditions. This network achieved a mean intersection over union of 0.84 on our synthetic test set. The predicted bounding box and center coordinates serve 2 purposes. They enable automatic cropping of the image around the satellite to minimize residual translation for the next stage, and they are passed forward as additional inputs to initialize the 6DoF pose model's translation estimates. This approach breaks down the problem, reducing the complexity of the final pose estimation task. Second, the 6DoF pose model. This larger network containing over 80 million parameters processes the cropped image to predict both rotation and translation of the satellite. Building on the GDRNet architecture from Wang et al. 2021, our model incorporates several key innovations. U-nets for image segmentation and depth map progression, creating dense 2D to 3D correspondences. A convolutional neural network that processes these correspondences, effectively replacing the traditional perspective endpoint algorithm. And a continuous 6D representation for 3DoF rotation with Gram-Schmidt orthogonalization as the final network layer, which both constrains predictions to valid rotations and significantly improves accuracy. Finally, the temporal Kalman filter. To refine the pose estimates, we apply a temporal Kalman filter to both the localizer output and the pose predictions. This filter uses past data to smooth out noisy predictions improving the stability and accuracy of our results. Our approach assumes a single instance of a single rigid object and requires a geometrically accurate CAD model for that object. On our simulated test set of 11,000 images, the model achieved a mean rotational error of 13.2 degrees with a median of just 2.7 degrees, a mean two-axis translation error of 31 centimeters with a median of 18 centimeters. Given that the mean target slant range is over 1,000 kilometers, translation error can also be expressed angularly as a mean of 300 nanoradians and a median of 170 nanoradians. A mean slant range error of 1.4% or 13.7 kilometers with a median of 1.2%. Most importantly, when tested on real data, our model successfully bridged the sim-to-real domain gap. On 105 frames of real video of the satellite CSat captured by a ground-based adaptive optics telescope, we achieved a mean rotational error of 4 degrees with Kalman filtering, and a reduction in maximum individual frame error from 57 degrees to 11 degrees when Kalman filtering was applied. You can see our pose estimate in red overlaid on one frame of that real imagery at the bottom right of the slide. Here are our references. Thank you to Research Computing at RIT for providing computational resources. In conclusion, our research showcases an advancement in practical automated satellite pose estimation, leveraging deep learning and data augmentation with the potential to provide accurate satellite pose in real time. Thank you for your interest in our work. Please reach out by email with any questions.